Hi, everyone. Do you hear me? Yeah, all right. Thank you all for being here. I'm very excited. This is my first time talking at PyCon. Today we're going to talk about Python and the JVM and how to make them talk with each other. So a little bit about me before that. My name is Shir. I'm from Israel. Conflicted, I know. Don't worry about it. I'm a Python programmer, a tech lead at Hunters, a security company headquartered in Israel. I've been there in the past 5 years, where I've been a Python developer, and now I'm a tech lead there, leading the ingestion efforts team. In my free time, I do poetry, music, transgender rights activism, and much more. What we're going to talk about here today, we're going to start with a bit of a rundown on why should we even want to combine these two languages, these two kind of foreign concepts to each other, the JVM, which is Java, Scala, Kotlin, and all other languages, and Python, which we all came here because we love. We're going to dive into a package that's going to make this magic happen easily. And by the end of the talk, we're going to see a real-world application used in production today that uses these concepts. So we are here, first of all, because we love Python, don't we? Yes, yay, Python. So we love Python because it's easy, it's readable, it's human. And we love its simple APIs, its completeness, its methodology, and everything in between. We love its paradigms, its flexibility, and we love that it's easy more than anything. We can write it, we can be tech people, we can be analysts, we can be researchers. Everybody knows Python. This is one of its greatest, strongest pros, and the reason that so many people love it. On the other hand, the JVM is great. The JVM is the underlying machine that runs Java-based languages. The biggest of them all is Java, of course, but it's not the only one. We've got Scala, Kotlin, Clojure, and many more. And they all run on the JVM, which is this underlying technology that powers them all. Now, why would we want to combine the JVM? Why should we care about the JVM at all? Well, for certain scenarios, such as the one we're going to look at today, the JVM can produce results up to 10 times faster than Python. I'm not the first one on this stage talking here today about languages being faster than Python, and I'm sure you've heard it all before. But Python being an interpreted language as compared to a compiled language has its pros and cons, and the major backdraw is its performance. The JVM, however, is compiled, and that makes its languages very fast and very efficient. Certain languages, such as Scala, were built from the ground up, focusing on optimizations of runtime, and JVM runtime in particular. And the ecosystem of world-class leading packages and frameworks that support the JVM is massive, to say the least. Today, the main example we're going to want to look at, for that matter, is Spark, Apache Spark, which is a large framework for handling massive amounts of data. So why not both? We have Python, which we love, which is simple, which is readable, which is easy, and we have the JVM, which is performant. We want to benefit from the both of them, get the best of both worlds, as the saying goes, and this is where Py4j comes for the rescue. Py4j is a package that we're going to dive into just in a minute that's going to enable this bridge between Python and the JVM. So let's see how it's done. The first thing we want to know when we deal with Py4j is how to deal on the JVM side. So today we're going to look at some Scala code where I come from, where my area of expertise is Scala and JVM, as well as Python. Scala is also the language that Spark is written at, which is the reason I specialize in Scala. and it's the main interface of Spark for the world. So when we take a look about a Scala application, it has a main function, main object, called app with a main function, and we want to initialize Py4j. We simply initialize a gateway server, it's called. Here it's very, very simple. We create this gateway server and we start it. And that's pretty much about it. Now we can connect to the JVM from Python. It's as simple as that. On the Python side, however, we need to set up our own gateway server, or kind of like gateway service. And it's going to enable us to access the JVM. It's a whole class path. When I talk about the class path, who here knows what the class path is? Okay, 50-50. So the class path is the way the JVM organizes its objects and classes in runtime, or like in compile time for the runtime. The way it works is just all of the code, all of the jars that the Java code recognizes are being written kind of into a file directory, so like kind of a file directory, and then it's all accessible from the runtime. So when a Java code references an object, it references something on the class path. It's as simple as that. It's kind of like Python namespaces, to compare it to Python. It's the global namespace of the JVM. So when we access the JVM, we actually access the class path, and then we can reference, for example, in here, scala.util.random, and just use this function even though it's a Scala function. It's not Python, which is great. We can then use it. It's just as any other Python code we've seen. But this is a bit cumbersome. This is gateway.java.scala.util.random. It's a bit of a mess. I'm sure we can do better. One way to do better is to import names to our Python namespace from the class path. The easiest way to do that is with the function java import, when we can just import JVM references to our local scope and use them later. I see some people are taking pictures. This is great. Thank you very much. Okay, this is great, but we can still do better. This is very boilerplatey. We don't want to import everything. We don't want to access everything ad hoc as we go. We want to be prepared. So this is all of the Python side, but there sure can be some improvements on the JVM side. Well, the JVM side has a functionality called an gateway object. Now, the gateway object is an object we can pass from the JVM to be a direct reference for the Java gateway on the Python side. So here we can import some very important app object and pass it to the generator, the constructor of the gateway server. This way, when we access it from Python, we just have the entry point variable, which is accessible to us everywhere. And it's going to be a reference to this application, to this object that we passed in the JVM. That way, we have access to it. We can just call its methods as if it was a Python object. Questions so far? Great. Okay. So let's take a look about a bit about the behind the scenes of all of this. So the way it all works is kind of like, as per the docs, is everything is a reference, and Py4j is kind of a quick way to run Python on the JVM. That's quoting the docs. The way we use that is that Python interpreter and the JVM, all of them have the instances of Py4j, and they talk with a bunch of proprietary custom interfaces and methods. They implement kind of like an RPC based on sockets with custom serialization for referencing data and objects on the JVM. That's a long sentence, bear with me. And the way it's maintaining its performability, quote unquote, we don't want to be the bottleneck here, is that it's all very local. We'll see later that it's not the only option we have. We can run it remote, but being it local first means that we don't lose any performance. Another caveat here is that what we pass between a Java application or JVM application and the Python application is references and not data itself. The data is being accessed in runtime, but what we pass from side to side when we communicate between the applications is references. If everything is a reference sounds familiar, this is also how CPython implements Python, basically. Everything in Python is a reference. It works in a similar manner. It's actually turning the JVM to be a bit Pythonian-like, more than the JVM is by default, by accessing everything as a reference. Almost nothing passes as a value, and this is allowing us to unify the serialization and deserialization protocols of these objects. So let's take a look at a real-world application. We're going to have quite a bit of hurdles to get there, but we're going to make it. So imagine the following scenario. This is a scenario I developed in my job at Hunters. Hunters is building a SOC platform. This is a platform for security engineers to manage all kinds of logs and interactions between security products. And I'm responsible for the team doing the ingestion part. So we take all the logs from all of these products and bring them in to Hunters. In this scenario, we have a use case where customers come, they want to onboard new data, and we want to show them what the data is going to look like in the data lake. So in order to do that, we want to run Spark jobs on demand. Instead of having a running application of Spark, a running cluster, we want to submit a job one time ad hoc, just to enable it to access the final results without pushing it to the actual bucket or to the actual sink. In this scenario, we chose to implement it with Py4j and enable us to access Spark runtime with a REST API, which we're going to see in a bit. The major concern here was why to implement the combination. Why bother? It's simple on the surface, but on the engineering perspective, it creates a dependency that we're not sure we want. It creates some kind of scenario where you need a Scala team, a Python team, and a team that knows to communicate between the two and to bridge the gap. We chose to do this, however, because of the benefits of both worlds. We have large content teams and integration teams that know Python and develop with Python and are familiar with Python, and we already had Spark running on Scala clusters and with Scala infrastructure running on the background. One way we could do this, and we didn't, is to implement a REST API in Scala. We didn't do it because we wanted to hand off the interface to the content teams for them to be able to develop it by themselves. So what we have here is a basic, very basic Spark runtime and definitions of a Spark cluster, a Spark job. What Spark does is it's setting up a server on one hand and queries it with all sorts of runtime operations to run in the cluster. In this case, it's not reading anything yet, but only defining a general job, a job that runs all the time without inputs, without outputs. So it just lives as an object in this case. So once we have this object, this Spark entry point, if you will, then we can start exposing it the way we saw earlier. we have this gateway server. We can expose we call it the on-demand simulator app. We can expose it, and then it will later be available from the Python side. Now, a question here is, which object should we expose? The way I see it is we want to expose the object that encapsulates the most business logic as possible. We want to make it so that the developing teams, the Python side, is exposed to the least amount of business logic code as possible. We want to ship a complete product to the Python side. If you know the acronym simple, lovable, and complete, this is what we want to achieve here. We want to push to the Python side a complete, simple object. In this case, it's this on-demand simulator app, which has one method, and it's run. It's accepting input parameters, output parameters, and that's all it does. On the Python side, we can start access all of our objects and inner models. We can import all of the Scala models we've built. We can run the application we've had, and we can access all of it through the JVM object, through the JVM gateway that we established earlier. The big decidable here is when we access the JVM objects is which one are we importing and which one are we leaving to the users to access with this cumbersome gateway.jvm.job request, for example. And my personal take on this one is that we should give whatever's trivial. If it's trivial, it should be given. If it's untrivial, or if, for another example, it creates a name collision, or even a mental name collision, like Python optional and Scala's option, I wouldn't want to import it because that would create confusion. In this case, we want to create since we're already creating a very complex scenario in here and we're combining two different languages, that not everybody are going to understand both languages. We are now on the Python side where people not necessarily know Scala or JVM architecture or anything. So we don't want to confuse them. So we want to leave whatever's confusing as a direct reference, and whatever that we think or is obvious that it should be trivial, we want to import in-house. So this is kind of the stage where we kind of leave the scope of Py4j. This is where Py4j gets us, and from here we get into Python development. So what can we do with this Python development? So as I said before, where I used to work, we connected this whole shebang into a fast API interface to make it accessible from the web for ad hoc requests, for simulating Spark jobs on demand. So kind of like, as opposed to Spark jobs that are long-lived running and streaming in nature, these are batch-based and accessible from queryable API. Something else we can do is work with a remote server. We can separate the client and the JVM. So the Python application can run locally on a machine that does not have the power to do the heavy lifting that Spark can do. And the Spark application, or the JVM application, can run on a strong server in the cloud or wherever. And thus we can gain the benefits of serverless architecture, kind of, without it being really serverless. Point to consider in here is that while I presented Scala code all over, Scala is kind of more difficult than just Java because of the way it registers because of the way it registers classes on the class path in the JVM. If we'd have time, we can get into it later. So this is kind of where we are at the moment. We've got this Py4j package to communicate between Python and the JVM. We've seen some examples on how to do that in a simple use case. We've seen some real-world examples. We've explored some options on how to do that and how to broaden the scope of what it can do. And this is a great time to stop for questions. Yes? Okay, I think there's a microphone that would be preferable so the recording can hear you.
So there was Jython before, and I was at Java 1 like 2 months ago. It talks about Graal and Java being interoperable with other languages. Does this work kind of take it a different route instead of focusing the efforts on Graal VM?
So I'm not familiar with Graal, but compared to Jython, and the products that actually combine the two languages, this is kind of making the app act as two separate processes. One of them is JVM-based, one of them is Python-based. And it doesn't have to force each of the languages to be a paradigm shift to the other languages area. So Python does not have to become a compiled language in a way, and the JVM doesn't have to kind of turn into an interpreted language. They can both live as their own beasts, and they just learn to talk to each other while they're running. So this is kind of like a different kind of perspective than Jython and other projects that kind of like compile a Python interpreter in Java, kind of like CPython being an implementation of Python in C and Jython being an implementation in Python in Java. This is kind of keeps the Python side pure Python, so it can be whatever Python you want. And the JVM-based, so it can be whatever JVM-based language that you want. In this case, it's Scala because it's the way Spark is written, but it can be Java, it can be Kotlin, Clojure, any other JVM-based language, because it works with the class path at its base without any other abstractions on top of it.
Okay, so it can't really take advantage of all the benefits of JVM garbage collection, like Shenandoah or generational ZGZ right now. Python stays in reference counting.
So you can benefit from that on the JVM side. The Python side is not going to be affected.
Thank you.
Sure thing.
Hi, thanks for your presentation. While I was watching, I was like, what about PySpark? So I'm curious, is PySpark doing anything?
That's a great question.
I think PySpark does use this, so I'm like, this looks kind of like PySpark, but is there more?
This is PySpark. I don't think we have the time, but if you open the PySpark repository on GitHub, it looks exactly like that. When I did this talk internally at the company, at where I work, we compared our code next to PySpark code, and it's annoyingly similar. Okay, it looks like code duplication. Py4j is so powerful because it is maintained by the Spark team, by the Apache Spark people. The only difference is that PySpark is indeed, or not the only difference, the only thing that PySpark does that this doesn't is that it expands and now is implemented in the form of Spark Connect, which is exactly this architecture of separating client and server. It is not implemented with Py4j exactly. It is implemented with more custom and more suitable solution, but PySpark is Py4j. Py4j is behind PySpark, and it's the reason we knew to approach Py4j in the first place. So that's a great question.
Thank you.
Any more questions? Okay, so we do have a minute to take a look at the way Scala is referencing, is registering its classes on the class path. So to those of you who had the unfortune to work with JVM bytecode, you would know that the JVM references classes in all sorts of different ways. And Scala references classes. Every class you define is attached, has a $sign attached to it at the end to distinguish it from Java classes. This is because Java classes are in many ways name overlapping with Scala classes. Scala is a superset of Java, and it being a superset, it uses some of Java's APIs, and it also overrides some of its APIs. So to make a distinguish, to distinguish between the two, then a $sign is added at the end. And then when you reference a Scala object or a Scala entry in the class path, you have to add this $sign at the end, and then kind of mess with its internals to get the actual module object. The way it's done here is we access the field, a field of the class that's called module, which is an internal representation in Scala for the module. It's kind of like Python dunder module or dunder file for the Python internals speakers. And we then return it as a field, kind of, but it's actually a reference to the module itself from within Scala. With that, unless there are any other questions, thank you very much for being here at this very difficult hour of the day. It's been a pleasure, and I'm very happy to be here. If you want to contact me, I'm going to be here for a few more minutes. You can talk to me on Discord. That's my personal site over there, and I'm available on LinkedIn. And thank you so much.